And then I don't know if you remember, but we said that torque is kind of like an angular force. So we can also sort of think of this torque as being a force, like an analog to force. They're not the same. I'm not saying that x is equal to theta, but I'm just saying that they're similar in a lot of ways, and we treat them in a lot of different ways. Now, we're also going to add another to this, and that is mass. And mass will be analogous to what we call the moment of inertia. Now, you remember mass was a measure of inertia. And if you recall back from Newton's first law, he defined what inertia is. All objects with mass have inertia. Mass is a measure of inertia. If you have more mass, you have more inertia. An object with a lot of inertia is hard to change its motion. That means the more inertia you have, the harder it is to change its motion. If it's going, it's hard to stop it. If it stops, it's hard to make it go. That's what inertia is. And in a similar way, moment of inertia describes how easy or how hard it is to set something into rotational motion. So for the linear motion, we use mass to describe the, hold on. And we use the mass to describe the inertia. For angular motion now, the moment of inertia. And we're going to use the capital letter I for moment of inertia. Describes the inertia of the rotating body. So the moment of inertia describes how difficult it is to change the rotational motion of the object. This is a very similar thing that we had for inertia, except now instead of talking about things moving in a straight line or in space, we're talking about things rotating around. But the same argument that we have, and all the same stuff applies, that if I have a big moment of inertia, it's hard to set something into motion. If I have a small moment of inertia, it's easier to set it into motion. Our moment of inertia, we're going to define in this way. It's going to be the sum of m times r squared. Now, this isn't really an equation, it's more of a definition. So the three little lines means is defined as, I don't know if you've seen that. Although we will use this as an equation, but we'll also see some other expressions for inertia. But just as a general rule, our moment of inertia is defined as the sum of mr squared. So I'll show you what that means, but first let me give you the units for inertia. The units, nothing fancy, it's just going to be kilogram meter squared. For kilograms, for mass, R is in meters, and so that's meters squared. Now R, which is similar to what we've seen already, is the distance from the axis of rotation to the mass. And what that means, like let's say I have an arrangement of particles like this, the r is going to be the distance from the axis of rotation, which is right here, to wherever my mass is. So in this problem, we're dealing with a set of masses, particular types of particles that have a certain mass. Later, we'll talk about regularly shaped objects like cylinders, spheres, stuff like that. But right now, we're just considering a set of particles that rotate about a certain axis. So for example, right here, this is my rotation axis. I'm rotating in this direction. My r for each of these is the distance from where the mass is to the axis of rotation. And so if I wanted to calculate the moment of inertia, it would be the sum of mr squared. And so now this is what the summation means, is that if I have multiple particles that are rotating around an axis, I just calculate mr squared for each of them, and I add them all up. So take just a moment and calculate the moment of inertia for these three particles. taking mr squared for each and then summing them up. I'll give you a head start and then I'll jump in there. All right, so our moment of inertia is going to be 3 kilograms times 1 meter squared. That's for the first particle. Plus 1 kilogram times 2 meters squared. Plus 2 kilograms times 3 meters squared. And so that's equal to 3 plus 4 plus, what, 18. And so my total inertia is 12 plus 18, or 30 kilogram meter squared. Something I want you to notice about this is that each of these masses contributes to the inertia by a certain amount. 25. I rounded up. I was doing, thank you. Louisiana people, they don't know what they're talking about. All right. What was I saying? Oh, so each mass contributes to the moment of inertia. But notice that the big mass contributes the least. And the small mass, the 1 and the 2 kilograms, they contribute more. And so you're probably scratching your head and saying, gosh, the big mass, that seems like it would give the most inertia to this thing that's rotating. But what's the difference here? The value for R. That the big mass is really close to the axis of rotation, and then these smaller masses are further away. And because I have this R squared, if I move away from the axis of rotation, it greatly increases my moment of inertia. If I double R, my moment of inertia increases by 4. If I triple it, it's 9, right? Because it's that quadratic relationship. So just notice that I then is proportional to R squared. And so the value R plays a lot of importance in dealing with in calculating the moment of inertia. In fact, more so than the mass. Now, with calculus, and we're not going to do it in this class, we do it in the other one, but we can calculate the moment of inertia for other objects. We can do it for this object because it's fairly straightforward. Let's say I have this hoop, like a hula hoop, right? Y'all know a hula hoop? My daughter can sit here and hula hoop just like this. She barely even moves. She's like this. She'll just sit here and the hula hoop will go around and around. Can y'all do that? It's me, I'm like, and it drops after like 2 loops. But anyway, this is like a hula hoop, and I want to figure out what is the moment of inertia. Well, the moment of inertia is equal to the sum of mr squared. And if I'm rotating about this axis, r doesn't change. It's always going to be the same. And what I can do is I can break this hula hoop into little masses. So there's one mass. So I is equal to m1 times r squared plus m2 times r squared. There's m2 right there. Plus m3 times r squared. And on until I add up the masses of the entire hoop. Now what I've done there is I've broken it into little pieces. Do y'all remember what those are called for your calculus class, when you break something up into little bitty pieces? No, you don't remember? Like differential elements? Y'all talk about that in calculus? Yes. Like whenever you write that dx or dt, that's a differential element. A really, really small piece of x, or a really, really small piece of t. And what this is a really, really small piece of m. Now, a summation, when you're doing a derivative, that's a slope, right? You're doing your rise over your run. But a summation, what is this like in calculus? What do we use in calculus to do sums of things? Oh yeah, Riemann sums, yeah, but that's the area, right? While we're doing area, what do we use to find the area? Area under a curve, yeah. The interval. Is that what you said, Megan?
Wow. Mississippi.
Mississippi, man. Famous people from Mississippi.
Calculus.
Okay, so you can do this, and we're not going to do it in this class, but you can calculate the you can calculate this just by doing the integral of r squared dm. So if you see this in calculus, you know the r doesn't change, so I can take it out, the integral of dm, and it works out to be that when I integrate over all of dm, I just get the mass of the hoop. This works out to be equal to mr squared if you do that integral. R doesn't vary with m, so I can take it out of the integral. The integral of dm is saying, what if I add up all these differential mass elements? Then I just get the total mass of the hoop, which I'm going to write as capital M. And so that brings us to this table, which you'll have. It's on your equation sheet. You probably saw it last time. Notice here's the hoop right here. I is equal to mr squared. It describes what that is. It's a hoop. It has a radius r. It has a mass m. And similarly, here we have a cylinder, a thin rod, rotating different ways. So this cylinder, I have a couple of different places here. The cylinder here is rotating about an axis through the middle of your head, or down through the long axis. And then this would be like a front flip, right? Remember the front flip that I did in class last time? Sorry if you weren't here, but it was awesome. It was amazing. All right, so this is rotating about a different axis. So as you encounter problems, which we'll see, you'll need to figure out what is the rotation axis. It'll say it in the problem. But is it rotating about this axis, or is it rotating about this axis? You'll need to figure that out, especially if you're dealing with a cylinder. Notice, too, we talked about this when we talked about axes of rotation. Which of these has the smaller moment of inertia? The cylinder rotating about the long axis, or the cylinder doing the front flip? Which has, just look at the equations, which has a smaller value for the moment of inertia? Which one? The top one, right. The one that rotates about this axis. Remember how we talked about it's a lot easier to spin around this axis? The reason it is because your moment of inertia is a lot smaller than about this axis. You got a really big moment of inertia about this axis because you have mass at big radii, right? Whereas right here, your radius is tiny. But about this axis, you got a radius of like 3 feet. And so that gives you a much bigger moment of inertia. Also notice here, we have two different spheres. One's a solid sphere, and one's a thin-walled sphere. Which do you think, given ones that are the same mass, would have the bigger moment of inertia? If I have two spheres, one thin-walled, hollow in the middle, and one solid, which do you think would have the bigger moment of inertia? The one that's hollow in the middle, or the one that's solid? You'd think so, wouldn't you? But we'll see if that's the one that's hollow. The one that's hollow has a bigger moment of inertia because you got mass at big radii. We'll see that question later. So this is our moment of inertia. Oh, let's do a little race. Here I have two hoops, or two discs. This is a little hoop. They're both the same mass. This one's made out of metal, this one out of wood, but they're made to be the same mass, and you can see they're the same radius, too. We're going to do a little race, and I want you to tell me which one do you think will win? Which one will travel faster? We'll do it back here. Which one do you think? The black, hollow hoop, or the wooden one? Do you think this one's going to win? It just looks faster, doesn't it? Don't you think? So this one, what's up? You're right here. Go over it. Good job. Okay, let's try it. Think about which one has the bigger moment of inertia. The one with the bigger moment of inertia is going to be harder to get started, right? And it's like it has a big mass. It's just hard to get going, right? So let's, I know you can't all see this, but that's which one won? The solid one won by quite a bit. And then they threw off. So this one has a big moment of inertia, and this one has a smaller moment of inertia. because this one has all of its mass at big radii, and this one has some mass at big radii, but it's spread all throughout. It also has some mass at 0 radius and all throughout. So this one has a much bigger moment of inertia. All right? Oh, let me show you a problem. Sometimes you'll be able to get things that have they're like different shapes sort of mushed together. And so let's watch this clip. This is from The Toy. Have you ever seen The Toy? You haven't seen The Toy? It was like from the 80s, but it's Richard Pryor. And you know, Richard Pryor, that guy should be from Mississippi because he's like a really, yeah, he's a good comedian. I gotta drop this Mississippi shit. Let's see, I'm gonna have to pull it up on YouTube. He's so famous, he's on YouTube. Right, here we go. Okay, so I want to figure out what is his moment of inertia. And so I'm going to treat this system as a hoop and a cylinder with the axis of rotation through the middle. All right, so I'm going to treat it as a hoop that has a certain radius and a certain mass, and then I'm also going to treat it as a cylinder that's rotating about this axis. Okay, and that sort of simplifies it, but it's also sort of like what we have. That we have, you know, Richard Pryor here. He's sort of like our cylinder, and then the hoop is the actual wonder wheel. And then if we want to know the total moment of inertia, I can just add those two up. So sometimes you'll see things, and we'll see this on the exam, where I have, say, a disc that gets combined with a rod, or a sphere that gets combined with a disc or a rod or whatever. And you'll have to figure out their total moment of inertia. In order to do so, you just add them up. So first we have to make some assumptions about the wonder wheel. I said the mass of that thing was about 10 kilograms. You know, about 25 pounds or so. And the radius, I said that the radius was 1 meter. So that's, Richard Pryor is about 2 meters tall, so the radius is about 1 meter. And then the moment of inertia of the hoop, I look on that table, and I find that it's equal to mr squared. That's going to be 10 kilograms times 1 meter squared. And so Richard Pryor, the wonder wheel, has a moment of inertia of 10 kilogram meters squared. Now, I also want you to calculate Richard Pryor's moment of inertia. And we'll say that Richard Pryor has a, oh gosh, what did I say? Yeah, we'll say that he has a mass of 100 kilograms. And if you look on your table for that cylinder, you need to know not only the mass, you also need to know the length. And so we'll say that the length, the distance from here to here, is 2 meters. And then you also need to know the radius. And I'm going to say the radius from here out to here, you know, it's roughly from here to here, maybe 20 or 30 centimeters or so. It looks, I assume, 30 centimeters. So the radius then is 0.3 meters. That's 30 centimeters. So now take a moment, look back at your table, and calculate what is the moment of inertia of Richard Pryor in this, treating him like a cylinder that rotates about an axis like this, where you're, you know, like a fort, like a flip. All right, so if you look at your table, you'll see that for the cylinder, my moment of inertia is this. Now remember, there is another cylinder, so you have to make sure that you get the right one. So this is 1/4 mr squared. That's going to be 1/4 of 100. That's his mass, times his radius, which is 0.3 meters squared, plus 1/12 mb squared. And that b is the length. So 1/12 of the mass, 100 times 2 squared. When I did this, I got 46. Is that what y'all got? What'd you get? 35, 58? 35? Okay, my notes could be wrong. I'm going to go with 35. We agreement? Okay, so 35 kilogram meters squared. Oh, it's 36 actually, if you round off. And then the total moment of inertia is this plus this. 10 plus 36. So the total I equals 10 plus 36, or 46 kilogram meters squared. We will encounter some problems later next week where we have to figure out the total moment of inertia. And this is the process that we'll go through. We'll see two shapes that come together, a sphere and a rod, or whatever the shapes are. They'll be on that table, and you'll need to figure out what is your new total moment of inertia. All right, let's try this quick test. We'll also see some questions on the next exam, kind of like this, where you have particles, mass of just particle masses that are rotating, and you have to figure out the moment of inertia. So let's try this one. Y'all could remind me at 11:35. You could just like very rudely start packing all your books up into your bag and stuff, and then I'll hand out your exam. Don't get out of order. I can't have your Just want to know the moment of inertia. This thing is rotating on an axis that goes down in between them. All right, let's go to about 1:30. Ask your neighbor. There's still about 25 of you that don't have the right answer. So ask your neighbor, see what they put. I'll stop at 150 actually. Let's stop at 152. Just guess if you're not sure. Okay, so in order to do this, we don't treat this as a regularly shaped object. We treat it as a system of particles. And so we say the sum of mr squared for each of the individual particles. The bars are 1 meter in length. So this is 1 meter. And this is 1 meter as well. That means the axis of rotation is 0.5 meters away. And then the mass of each is 1 kilogram. So I'm going to have 1 kilogram times 0.5 squared. And since there are 4, I'm just going to multiply that times 4. This only works. I can only multiply it by 4 because all the masses are the same. And also, all the masses are the same distance from the axis of rotation. As you look back through the old exams, you'll see variations of this. I can have different axes of rotation too, like I can have an axis of rotation through there, you can have it down through the middle, and you have different shapes as well. So I would look back at some of those. You'll certainly see a question like this on the test. So this answer worked out to be, let's see, that's 1/4 times 4, works out to be 1, which is D. And let's see, a lot of you put B. I don't know why you put B. Anyway, the answer here is 1. Okay, that's kilogram meter squared. Let's do a few more in the back, and then we'll keep up with this. Here we have 2 spheres. They have the same radius, and they have equal masses. Same mass in both these spheres, and they're the same size, the same radius. But one is aluminum, and the other is made from gold. Gold is a lot more dense than aluminum, so the golden sphere is hollow. Which of these has the bigger moment of inertia about an axis that goes through its center? Solid aluminum sphere or the hollow gold sphere, or they both have the same. I mean, they're the same mass and same radius. So, all right, let's stop at 55. Okay, awesome. B is right. The hollow gold, because you have more mass at bigger radii. I is mr squared. Our basic definition is that I is the sum of mr squared. So if I have more mass at bigger r, that means it's going to have a bigger moment of inertia. Let's see if the next one's short. We'll come back to this. Okay, I'm going to hand out your exams. I'm going to do it like I usually do, where I lay it out on the floor up here, and you guys just come grab it. Marco Rodriguez.